We're going to be working on the back of the cheat sheet. It's actually the very last section called How Do I Find Percent Yield? There's a funny little thing that happens in life in regard to what a system should be able to produce, what it's built to be able to produce, and then what it actually produces when the system runs. For example, I know that most of y'all are too young to have done your own car shopping yet, but one of the big factors that a lot of potential car owners look at when they go shopping is what the miles per gallon of the vehicle are. The idea being is that if it gets 30 miles per gallon, for every gallon of gas you put in the car will go 30 miles. That's pretty good versus like a truck that gets like 14 miles per gallon. Well, you're going to be spending a lot more money on gas because you'll have to fill up more often. But here's the interesting thing about the way cars are advertised. Let's say a car is advertised to go 30 miles per gallon. You see it on the commercial. This car goes 30 miles per gallon, which is pretty good. You don't have to write this, just listen. This would be what I would call the theoretical yield of the car. On paper, the way they built the car, it should go this many miles for every gallon you put in it. Now, the phrase theoretical yield should strike you as familiar because remember the answer to all of the stoichiometric grids we've done so far have been called a theoretical yield. But here's the sad truth. They're lying to you. The Ford and Honda and Nissan, they're all lying to you. This car won't go 30 miles per gallon. It actually might only go something like 27 miles per gallon. I would call this the actual yield. This is what it does when you drive it. The reason that there's a difference between these two numbers and the reason they're allowed to lie to you is because some of the energy that the engine should be using to go towards going miles gets used elsewhere. The engine's capable of doing this. But when you do other things like start the ignition or run the AC system or the other things that the car does, or just the fact that it gives off heat and loses energy like that, it doesn't reach its full potential. And it actually does something less. We could find out something called a percent yield by looking at these two numbers. The actual yield, by what the car really did when you drove it, versus the theoretical yield on paper, what the mechanics said it should be able to do. And if you look at your cheat sheet or on the whiteboard over there, you'll see that the equation for finding percent yield is we divide the actual by the theoretical times 100. So if we did that real quick here, the actual yield was 27. The theoretical yield was 30. Somebody find this answer for me. You can do it all as one function. 27 divided by 30 times 100. What is it? 90. 90%. So this car is getting 90% of the efficiency that it's supposed to, which is still pretty good. We're not really supposed to expect perfection because any system loses energy in the form of heat and other factors. Any questions about the analogy here? We can apply this same idea to any chemical reaction. For example, if I just make up a reaction here, go ahead and write this down. All right, there's a reaction. Let's say that we do a grid, all right, and there's a bunch of data in these squares as usual, moles and grams and given compounds and values, and when it's all said and done, we get an answer. We put it into our calculator, and it spits out the answer 70. That's a naked number, but what do we call that answer? A theoretical yield. The biggest thing to understanding this percent yield thing I'm talking about is to simply understand that when you do a grid, remember, it spits out a theoretical yield, always. It spits out this bottom number that we would be using. Think about it. Think about the car analogy. How would we find an actual yield of this reaction? What would we have to do to get an actual yield? Not to find percent yield, to find an actual yield, a number. In order to find that value, we would have to go do the experiment. Remember, to find the actual yield of the car, you have to go drive the car. In order to find the actual yield to compare this to, we would have to go to the lab, put our goggles on, get some hydrogen, get some oxygen, and actually run some numbers. Write this down in your notes. Actual yields are found in the lab. Actual yields are found in the lab. Now, if you take a look at your cheat sheet, it'll reiterate the things I've said so far. It says the percent yield is the final percentage of product made compared to the amount expected. The actual yield is the amount of product physically calculated in the lab. So based off this made-up example, let's say that we had our goggles on and we went and we mixed stuff together, and when we measured out stuff in the lab, we got 45 grams, or we'll just not make it so naked. All right, we held it in our hands. We said, hey, look, this reaction made 45 grams. Here it is. Well, that would be my actual. Because I didn't get that number from a grid. I got that number from actually doing the reaction. And then to find percent yield, it would be the actual, 45, divided by the theoretical that we did get from a grid, 70, times 100. And I get 64.29%. Which means in this totally made up stuff, we got about 64% of what we should have gotten. Now let's apply this to the way you would actually see a question. Write down the reaction that I have projected here into your notes. For those of y'all at home, this is the first problem we're doing. You can pause the video if you need to write down the stuff. Copper 2 iodide reacts with potassium nitrate to produce copper 2 nitrate and potassium iodide. It's not balanced, which is never okay, so I'll balance it for you, but remember, you should be the big balancer. We'll need a 2 there and a 2 there, it looks like. A 1 to 2 to 1 to 2 mole ratio. Now, look at the question. It says, you react 25 moles of copper nitrate and produce 7,115 grams of copper 2 iodide in lab. See how there's two given numbers? In a percent yield problem, there's two values that are given. One of those values, look here, one of those values is the actual yield. In order to have an actual yield that you actually do in the lab during these problems, it has to give you one. Otherwise, it would have to say, go to the lab, get out some chemicals, and mix this stuff together. We obviously don't have time to do that. We're going to do it in a lab next week. But for the most part, for the online part, I have to give you a value for the actual yield because you're not doing a reaction. You're not doing an experiment. And the only way to get an actual yield is to do an experiment. So look closely at that question. One of those numbers is the actual yield. And the key phrase is in the lab. See if you can figure out which one is the actual yield. Which one is it? The big one, right? 7,115 grams of CuI2. Because it says that this guy was made in the lab. This is the actual yield that we don't need to do anything with yet. What we don't have is a theoretical yield. But we've already learned how to find the theoretical yield. We just need to do a stoichiometry problem. So now let's do what we always do. That other number, the 25, is a given for us to use. Right after the number 25, it says moles of CuNO3, 2. I took my given number and the information that came right after it. For the unknown that we're going to go to, listen close. We want to use all the units of the actual because what we want to do is create a theoretical that we can compare to that actual. So for the unknown, it's going to be grams of CuI2 because we want it to match all of the units of the given actual number. And now we need a theoretical yield, so we need a grid. This is a what-to-what problem. Moles to grams, because of the way it's asked. Look on your cheat sheet, find the moles to grams grid, and you'll see that it is the second grid listed. So I'm going to draw the lines of that grid. You do it too. See if you can do it without looking at mine. I still have the steps on how to fill in the grids listed on that whiteboard if you find it helpful. Step 1 is to, well, once we have the grid drawn, we need MOLs and Gs in the proper squares. Look at your cheat sheet. We're doing moles to grams. I see this. Stop me if I do anything weird. Then we go back and enter the compounds, whether it be given, oops, there's a grams here. Whether it be the given or unknown compound, this grid asks for the given compound in these two squares. The given compound is CuNO3 2, nice and long. These three squares on my cheat sheet grid ask for the unknown compound. The unknown compound is CuI2. Copy the cheat sheet carefully. This value here, it says given, which is 25. Going straight across the top, it asks for a coefficient here of CuI2. CuI2's coefficient is a 1. To here, it says periodic table. So we need to know the PT mass of CuI2. He's comprised of copper and iodine. There's 1 copper and 2 iodines. look to your periodic table, and you'll see that copper has a listed mass of 63.546. Iodine has a listed mass of 126.904. My 1 copper will keep the same molar mass, but my 2 iodines come out to 253.808. Of course, remember, we're in a PT square right now, so we're adding up the molar mass of CuI2. Comes out to 317.354 for the total mass. Everybody okay with that step? Review from last unit, of course. 317.354. Down to the bottom, check your cheat sheet. It says the coefficient of this compound, which also happens to be a 1. And then this square is always a 1. Multiply across the top. 25 times 1 times 317.354. And you're going to get a top value, but if you notice, the bottom values are both 1s. 1 times 1 is 1. So you are supposed to divide by the bottom, but you're going to be dividing by 1. So you can go through the step if you just like to see it. But your final answer here is 7933.85. Any questions on anything we did? It was just stoichiometry. But what's the question? Look, what's the question? Find percent yield. Remember what it is we're doing. Percent yield is actual divided by theoretical times 100. There's a number here that we've still done nothing with, because at the very beginning we saw the phrase in lab, we identified him as the actual, and now we're finally ready to use him. Make myself some more space here. The actual is 7115. I'm supposed to divide that by my theoretical, which, remember, is the answer from my stoichiometric grid. 7933.85 times 100. Get that final answer for me. So did I. Your units is percent. So again, understand that in the reaction that I've now halfway erased, but it's up there, it said we should get 7,900 grams. That's what we should get. But when we went and did the lab, we only got 7,100 grams. Not what we should have gotten. But comparing them together, we got about 90% of what we were supposed to get. Let's do another one. Here's the next reaction that we'll be doing. I'll balance it for you, but you should be making your lists and such. We need a 2 almost everywhere. 2 to 2 to 2 to 1 mole ratio. And now we're balanced. Take a look at the question. The moment that you see that it's asking for percent yield, you need to begin by picking out which of the numbers that's listed is the actual yield. So don't say anything out loud. Look at the way it's worded, and in your notes, somewhere off to the side, identify the actual yield that we will not use until the very end of the problem. What did you pick for the actual yield? 1.99, because it's the one that is found in the lab. So, again, off to the side, 1.99 moles of CS is my actual, because he's described as being found in the lab. We cool there? The other number is the given number. And in this case, it's 2.2 grams of H2. So there's all of the given stuff that will go into our grid, because we have to find the theoretical to work with our actual. What are the unknown units? Moles of CS. Remember how we find that? Again, we want our unknown units to match the units of the actual. So there was the actual. All right, we don't care about that number right now. But moles of CS is what we want to get our answer. Guys, this is a grams to moles problem. Find the theoretical yield. Let me know if I can help you. If you're struggling with stoichiometry in general, now is the perfect time to call me over. You can pause. We agreed it's a grams to moles problem, so I'm going to go ahead and pull out my grams to moles grid. It's the third grid on your cheat sheet. Looks like this. The biggest breakdown I still see as I go around and help y'all is that you put the information into these squares in the wrong order. Monkey see, monkey do. Decide that you're going to see the order that I do this in, and don't do your own order. G's and MOLs first. I have it on that board over there. G's and MOLs first. It looks like this. Then the compounds. Those of y'all that start putting numbers in, if you put 2.2 in that square next, you're doing it wrong. Don't do that. I need more letters in these spots. If I look at my cheat sheet, all four of these squares say given compound. The given compound is H2. This one square says unknown compound, which is CS. Now we can go back and put those numbers in. This square says given number, which is 2.2. This square just has a 1 in it, always. This square says the coefficient of cesium. Cesium's coefficient is a 2. Down to the bottom, it says periodic table. We need 2 H's. 2 H's have a mass of 2.016. H plus H. My final square wants the coefficient of H2. He's the only one without a coefficient, which means it's a 1. Multiply across the top. 2.2 times 1 times 2 is 4.4. Multiply across the bottom. 2.016 times 1 is 2.016. Divide the top by the bottom, and I get a theoretical yield of 2.18. Theoretical yield, remember the answer to any grid is a theoretical yield. But even though I've got two numbers circled right now, I still don't have an answer. The question says, what is the percent yield? So actual divided by theoretical is what we need to do here. My actual is 1.99, the number that we have not yet used since we've identified him, divided by my theoretical that we just calculated, times 100. Did you get 91.28?